searching algorithms. If you did not take computer science principles, then definitely spend a little bit more time in this. This is talking about how a computer actually looks through and finds things that you go and tell it to and targets. So we're going to look at linear and binary search algorithms, and we're going to look at the best and worst case scenarios and the time that it takes to find those. So here's a challenge. We're going to play a game. If you click on this box right here, it actually will launch the game for you, and read the directions and then find out what the challenge is. So these boxes are in random order. Out of the 5 boxes, we're looking for the number 138. It's different every time. And you have 6 guesses to find it. So here, I'm just going to start over here because they're in random order. Hey, look, I found it. I'm going to restart this level. Again, random order. Out of 5 boxes, I still have 6 guesses, and now I'm looking for 498. Remember, they're in random order, so I'm just going to click down until I find. I've got 3 more guesses left, and I found it. So I can go on to the next one. These boxes are in random order. I have 9 boxes, and I've got 10 guesses to find it. I'm looking for 187. Again, I'm just going to go down the line until I find my goal. These are out of order. Oh, so close on that one. I've got 3 more guesses. Worst case scenario on that one. So I took 9 guesses and I only had 10 guesses in order to find it. So that's just kind of searching, and this is looking at a linear search, going from one object to another. All right, let's try this again. So now we're going to change it slightly. This time we're going to have less lives, which makes it a little bit more challenging, but this time the numbers inside the boxes, they're going to be ordered. So the number from the farthest left is going to be the smallest, and you know that this one's going to be the largest. All right, so going back to where'd it go? So going back here, so if we go to our next level, this time they're in sorted order, but I only have 5 guesses. So think about what is the best way for me to use those 5 guesses if I know that these are in sorted order. Am I going to start with that box number 1 again, or am I going to start at the end box, see what the biggest number is? Is there a better way to search through these? Not the one I wanted to go to. So play around with this game for a little bit. This will give you an idea of linear and binary search. And we're going to watch some videos. So this video is looking at a linear search and a binary search.
We use computers to do hundreds of different tasks every day. Things like searching the internet, editing an image, or finding a route on a map. But have you ever wondered how a computer figures out how to do these things? An algorithm is a step-by-step process which tells a computer how to do a specific task. But there can be many different algorithms for the same problem, kind of like how there can be many different recipes for baking a cake. But as we know, some recipes can be a lot better than others. So we're going to do a little experiment to see if the same thing is true for algorithms. Here we are in front of the University of Canterbury Library, about to start the great algorithms race. Competing today, we have Speedy Spencer.
So I'm actually not going to go through this whole video with you. So this is also showing the difference between a linear and a binary search. So one of these guys goes down into the library to find a book, and he searches through all of them. Another one actually uses a more targeted search to kind of figure out where the book is going to be in the library. But it's kind of a fun little joking video about again, algorithms and binary computer searches. Here's another video, and this one's a little bit shorter.
Say you have a large amount of information in an array or list, and you're looking for one value in particular. In order to find that one value, you need to search through the array or list for that value. There are a few ways to do this, the first and simplest of which is called a sequential search. A sequential search is exactly what it sounds like. You typically start with the first item in the array or list and move progressively through it, one item at a time, until you find what you're looking for. While effective, this method can be inefficient, especially if the item you're looking for is towards the end or not even present. The most efficient searching method we have is called a binary search, but it can only be used on data that is already in order. In a binary search, we actually start in the middle of the array and then keep narrowing the search depending on whether the value we're searching for is larger or smaller than the one we're currently at. This is a vastly more efficient method because it allows us to eliminate half of the remaining values each time we access a value. Thanks for watching.
So that was a pretty short and straightforward video on binary versus linear search. Stop playing. All right, so let's look at sequential and linear search. So sequential or linear search is the same word, and it typically starts at the very first element in an array and looks through all of the items one by one in turn. And it's actually kind of what we've been using in like going through the searches. If the desired value is found, then the search returns the index at which the value is found. If it doesn't, then the search returns -1, and that indicates that the array or the list did not have the target that we were looking for. So a key point with a sequential search is that this is the only search that can be done on an unsorted list. So if you're just throwing a bunch of information, you'll have to use a linear search. However, if you have a list that is sorted with information, then you can use a better search, which is a little bit faster. So take a look at activity 7.5 in the code. And what if the code inside the loop was modified to be instead, if elements equal targets, then return J, else, and that's the change right there, else return -1. So put in that else and see what happens, and just take a look at that. This code will run automatically, and pass the test if you just run it as is. If you put in that else, there's errors. So taking a look at the multiple choice, what will cause the longest execution of a sequential or linear, which is where you're going line by line, item by item, looking for a value of an array of integers. So which is going to take the longest time. If it's the first one, no, then it stops right away. If it's the middle, no, it's going to be in the middle. There's more after. If it's the last one, oh, that's promising. Well, what if the value isn't in the array? It's actually that one. So why isn't it C? And that's because it has to check all of them, has to check that very last one, and then confirm that it's not there. Remember, we get that -1. What about, what is going to cause the shortest time for a linear search? Well, that would be if the first one turns out to be the target that you're looking for. All right, so what if we were searching for an array of strings? What would be different? And you can look at activity 7.1.5 for looking at strings. And what if the elements of the array list instead of the array, what would change? And I'll give you another example in a little bit. So what if I said that I could absolutely guarantee that that one of you is thinking about a whole number, 1 through 10, inclusive, and I can guess it in a maximum of 4 tries? Well, if you look at it, this would be 1 all the way through 10, and I can guess it in 4 tries by using a binary sort. How would this task be performed if a linear search? Well, if it's a linear search, then I'd have to guess 1, 2, 3 until I get that target. But in 4 tries, what I can do is I can just guess the middle of 1 through 10 and then know if it's higher or if my target is higher or lower. So a binary search can only be used if the data is sorted in order. And what it does is it just keeps dividing the sorted search space in half until it finds that target. It compares the target value to the value in the middle of the range indices and decides if it's higher or lower, and then searches again in that middle. If the value isn't found, then it looks again on either the left or right, depending on if that target is higher or lower than the values that it's looking at. Each time it loops through, it eliminates half of the search. So if you've got 1,000 things, then suddenly you're cutting that in half every time that you're looking for that item. So let's take a look at this in action. So again, you can look at this and you can play around with this. You can enter a key as a double value. So press the step button and perform a comparison. So you can take a look at that. It's kind of fun. So again, looking at binary search algorithms. The binary search calculates the middle index, the left plus the right, divided by 2, where it finds the middle, where the left starts out at 0 and the right starts out, so the right side starts out at the array list length -1 to get that very last, the index of the last element. Remember that it is that the division gives a integer result. So 2.5 becomes 2. And that's actually kind of important to figure out which side or how many guesses it's going to take. Then the algorithm goes on to compare the value to that middle index with the target and then decides which side to continue looking for. If the target value is less than the value at the middle, it sets right to middle -1. If the value is greater than the value at the middle, it sets left to middle +1. We're going to take a look at what this looks like in a second. Otherwise, if the values match, then it returns that middle index. It also stops when left is greater than right, which indicates that it wasn't found, and so it returns a -1. So you can take a look at what it looks like on 7.5.2.1 in this binary search. And memorizing the code isn't necessary, but understanding the algorithm is needed. So let's take a look at this. What if we're searching for an array of string values? So what changes? Let's take a look. So here's our string values. We've got target compared to elements middle is less than 0, and then target dot compared to elements middle is greater than 0. So again, here is our what changes. The main difference, and this is crucial, and between the linear and binary search is that sequential search can only be used if this is the one that is the only search that can be performed with an unsorted list, and a binary search can only be performed on a sorted list that has the values in order. So take a look at this. Given an array of apples, bananas, cherry, kiwi, and watermelon, how many times would it take to loop through to find cherry? What about apple? And so forth. What would be the middle of the list if cherry were removed? So that middle one, what would become the middle? Well, think about what an integer in doubles would be. So the middle would become integers 0, 1, 2, 3. And you take 3 divided by 2, be 1.5, but then that 0.5 truncates, so you get that index 1 is the middle. All right, so I'm actually not going, for time's sake on this video, I'm not going to show you this, but this is actually a really great computer science video overall. It really covers a lot of what's covered in computer science principles, and this, the Harvard students will actually do a search and sort for linear and binary search starting at 20 minutes in. So if you want to play this, by all means, watch all 45 minutes of it when you have a chance, because it actually is a good video. But 20 minutes in is where they start to talk about the difference in searches and sorts. We're not going to play it right now. So when you watch that video, what you're going to do is that you can reuse part of an algorithm within an algorithm, and that gives the idea of recursion. And we're going to actually talk about that more in a couple of units, but that gives you the idea of using an algorithm within an algorithm to kind of, that's the recursion idea. So runtime and worst case scenario, because these are important to kind of grasp. How do we choose between two algorithms to solve the same problem? And that's when we're going to evaluate them. So for a searching problem, it depends on your data. It also depends on the characteristics of the algorithm and what it's looking for. Runtime is a vocab word, and it's the measure of how fast an algorithm runs on a given set of data. So it's how fast it will take. Binary search is much faster than linear search, especially on really large data, but it can only, again, be used on sorted data sets. With runtimes, computer scientists will often think about the worst case behavior, so the very last element, or in most cases, the element's not found. With searching, the worst case is usually when you cannot find that item. With the linear search, you have to go through the whole array list before realizing that it's not there line by line, item by item. In a binary search, it's much faster, even if the element's not there, because it just eliminates half the data every time it steps through. Informally, we can measure an informal runtime simply by counting the number of steps that it takes. So here's a comparison. So with a linear search, if you have 2 items, it's going to take 2 comparisons. And a binary search is going to take 2. Remember, binaries get stronger and faster the bigger the amount of data that you have. So if you have 4 items, and a linear search is going to take all 4 times, going through all items in that array. For linear search, you actually get to take 3 searches because you get to divide by half every time. For 8, you get to, for linear, it's 8. So if you notice, every time with linear, it's however many items are in that list. For worst case scenario, remember is what we're looking for. For binary, we're cutting it in half. So essentially, it's how many times can you take 100 and divide it in half until you come down to not being able to divide it anymore. You can divide 100 in half, by the way, in computer science 7 times. So it also can be described in mathematical functions where the array is the size n, and the linear search runtime is a linear function, and the binary search is the function of log 2n. This is called a big O runtime function, and so here's an example of this. And here's a quick video that I think it's about 5 minutes long that talks about big O logins. Is you need to know the concept, but not necessarily like you need to know which one's faster.
Today we're going to learn about
I'm
big O
going to check on
notation.
what time it is. I was right, 5 minutes.
So what is it?
For
Big O
again, for the sake of this video, I'm not going to play that video inside of my video because I'm almost done. So counting steps. You don't need to know the login runtime on the AP exam, but you should be able to calculate how many steps binary search takes for given n. So you can do this in a couple of different ways. You can count how many times it takes you to divide the number in half, or you can start at 1 and keep a count of how many times you can double it within the powers of 2 until you reach the number that is slightly above that target, above your target. So there's 2 different ways. You can either divide everything by half or count up multiplying by 2 until you get to that target. So you don't need to know the log n on the AP exam, but you do need to know the binary. So if you had an ordered array of 1,000, what is the maximum number of iterations, times going through, required to find an element with binary search? Remember, it's always assuming worst case scenario. So it's how many times can you divide 1,000 in half or multiply everything by 2 until you reach, it's 1,001 because you have to go slightly over it. Whew. All right, so with a partner, work through 7.5 challenge on CS Awesome. It's a spell check challenge, and it actually looks at how many times it takes a computer to check through a dictionary to see if a word is spelled correctly or not correctly. And here's your summary. So there are standard algorithms for searching. The sequential linear search is search algorithms that check each element in order until the desired value is found, or all elements in array list have been checked. The binary search algorithm starts in the middle of a sorted array and then eliminates half of that array every time until the desired is found or until all elements have been eliminated. In order to use a binary search, the data must be in sorted order, and this is going to be covered more in Unit 10. An informal runtime comparison of the program code must be or can be made to use statement execution counts to see what or how good an algorithm is. So make sure you look at 7.5 in Runestone, complete the self-checks, and if you need any additional resources, here are the links to the AP Daily videos here, and then your AP alignment.